And that table, my friends, is called the cumulative distribution function table for the standard normal random variable. Now, that table is that table, but I am just going to show a different version of it to you. Now, let's just check the CDF table. Here we have the picture, the plot of the probability density function of a standard normal random variable. Now, if we are interested in calculating the probability of Z, a standard normal random variable, to be less than or equal to X, we need to integrate this probability density function from -infinity to X value, which is the total accumulated area on the left-hand side of X. And this is also called the CDF of a standard normal random variable at X, right? So this shaded area is the probability of interest, which is the probability of a standard normal random variable to be less than or equal to X. Now, the blue table is just giving us the answers of such probabilities for any positive X value. For example, if X value here is 0, which means the X value is just here, in that case, the total area on the left-hand side is 0.5. Now, let's just say we are interested in calculating the probability of Z to be less than or equal to 1. So in that case, you need to check that value. So the probability that the standard normal random variable is less than or equal to 1 is 0.8413. Let's just say we are interested in calculating the probability of Z being less than or equal to 1.5. Probability of Z being less than or equal to 1.5, it is here. If you're interested in calculating the probability of Z being less than or equal to 1.05, then the probability of interest is 0.8531. So basically, this table is read from left to right and top to down, and the cumulative probabilities are always increasing as you move, okay? And you can identify any cumulative probability by looking at this table, and we are just going to practice this in a few questions that we are going to solve later. And another thing about this table, after 2.99, the convergence becomes very significant, and the cumulative probability gets very close to 1. However, if somebody asks you a cumulative probability for any point that is greater than 3, still the answers are here. Even though the values are very close to 1, still you can answer these questions. But you see, according to this table, the probability of a standard normal random variable to be less than or equal to 3.9 is approximately equal to 1. So practically, it is almost impossible for a standard normal random variable to be greater than 3.9. It has a very, very insignificant probability. So this is the CDF table of the standard normal random variable. But one issue here is, if somebody asks us the cumulative probability or the probability of a standard normal random variable to be less than or equal to X, where X is not positive but a negative value. So let's just say X is on the left-hand side of this picture, and the cumulative probability up to that point is just going to be less than 0.5. The answer is not directly available in this table. So this table does only show the cumulative probabilities for positive X values. But if we want to identify the cumulative probabilities for a negative value, so it is also possible by using this function. But we need to apply an indirect approach. All right, so you see, this table shows us the cumulative distribution function of a standard normal distribution. Therefore, it is shown as a capital phi of X, which indicates the probability of a standard normal random variable to be less than or equal to X for many X values which are positive. However, we can use the symmetricity of this probability density function, and because it is symmetric around 0, it is also possible for us to identify the CDF values for negative X values by using these probabilities as well. Now, let's just say somebody has ask you a probability related to an X value, which is not directly available in this table. For example, if somebody asks you the probability of the standard normal random variable to be less than or equal to 1.55, you will say that the answer is 0.9394 because 1.5 is here and 0.05 is here. The probability of standard normal random variable to be less than or equal to 1.55 is 0.9394. Now, if somebody asks you the cumulative probability up to 1.56, the answer is also here. But what if somebody asks you the cumulative probability at 1.557? So that value is between 1.55 and 1.56. And because the CDF function is a monotone function, which is always increasing in the form of an S shape, you can interpolate these 2 points and apply a linear approximation between these two and identify that probability approximately as well. So this means we can use linear interpolation between the closest values if the X value does not directly exist in the table. And also, we can use this table in the inverse direction as well. So not in every question, somebody will give us an X value and ask us to determine the probability. Sometimes the question will give us a probability and it will ask us to determine the X value regarding to that. Now we are going to practice all of this in the next question. So these examples are very easy examples. Please try to understand them carefully. You will realize that it is not very hard. However, they certainly need your focus here. So I have a standard normal random variable with location parameter 0 and scale parameter 1. So the first question asks, what is the probability of z being less than or equal to 0.34? So this first question is easy. I am going to check the CDF table. It asks me the probability of z being less than or equal to 0.34. And I need to identify x as 0.34 here, 0.34. So this is my answer. So the probability of a standard normal random variable to be less than or equal to 0.4 is the area on the left-hand side of x, which is 0.6331. And that is here. Let's do an example which is a little more complicated. Now it asks the probability of z being greater than 1.667. This time we have 3 digits after the decimal point. What is the probability of z being greater than 1.667? First of all, this is a tail probability, right? It is not a cumulative probability because it says greater than. Now let's look at the answer. The probability of z being greater than 1.667 is 1 minus the cumulative probability at 1.667, which is 1 minus the capital phi at 1.667. I need to identify the probability at 1.667. And that is, as you can see, I have the cumulative probability at 1.66. And I have the cumulative probability at 1.67, but I do not have any cumulative probability for 1.667. So what am I going to do? I am going to apply a linear approximation. So I know that the CDF is equal to 0.9515 at 1.66. And I know that it is equal to 0.9525 at 1.67. So I know that this function, the CDF, is not linear actually. However, in this narrow interval, I can approximate it linearly. I can just connect these 2 dots and I can assume that at 1.667, I can find the response value, which is the CDF at 1.667 with linear approximation. So what is it going to be? First of all, I know that because the CDF is an increasing function, it is never decreasing, it is always increasing. I know that I can make proportions between 0.9525 and 0.9515. I know that the response at 1.667 is somewhere between these 2 values. So what I'm going to do is I am going to take an average of CDF at 1.66 and the CDF at 1.67. Now you see the distance between 1.667 and 1.67 is 3 units and the distance here is 7 units. Therefore, the proportions of these distances should be the same as in here. Okay, so here we should have a 3 units of distance and here we have a 7 units of distance. So what you are going to do is this. You are going to multiply 0.9525 with 7 and 0.9515 with 3 and summation will be divided to 10, which means you are going to take a weighted average of the 0.9525 and 0.9515. However, the weight should be inversely proportional to the distances. If I have 3 units of distance here, I need to multiply the phi at 1.67 with 7, and I have to multiply the CDF at 1.66 with 3. And the response will be approximately 0.9522. So I can approximate the CDF at 1.667 by taking a weighted average between these two values, and that is going to be 0.9522. And remember now, originally the question was asking the tail probability, not the cumulative probability. So we have found the cumulative probability here. That is not our answer. Our answer is the subtraction of that cumulative probability from 1, which is the tail probability, and that is 0.0478. So in part C, we have a standard normal random variable Z, for which we would like to calculate being greater than or equal to probability from minus 1.08. You know, in continuous random variables, greater than or equal to and greater than probabilities are the same, right? So even if we have an inequality or a strict inequality, we always get the same probability because we do not have any positive probability at equations. So as you can see this here, the probability of Z being less than or equal to X is the same as the probability of Z being less than X. So they are the same. I do not care if I have an inequality or a strict inequality if I am dealing with a continuous random variable. Now, let us calculate this third probability, which is the tail probability at a negative value. So the probability of Z being greater than or equal to minus 1.08 is what? So let's draw the plot diagram. This is the plot diagram of the standard normal distribution. It is perfectly symmetric around 0, and minus 1.08 is here. So this probability, Z being greater than or equal to minus 1.08 is what? It is the area on the right-hand side of minus 1.08, right? Now, I have a perfectly symmetric probability density function. If you take the symmetric probability density function by putting a mirror in the middle, then that area will be the same area as the area on the left-hand side of positive 1.08, right? If I have a perfectly symmetric probability density function around 0. So the probability of Z being greater than or equal to a negative value will be the same as the probability of a standard normal variable to be less than or equal to the positive counterpart of that value. And that is basically phi at 1.08. Because it says greater than or equal to this negative value, I draw it and I have determined the area that I need to calculate, but I know that due to the symmetricity, that area will be the same as the area on the left-hand side of the positive counterpart of that value, which when you look from the table, which is the CDF at 1.08, which is 0.8599. Now let me show you that here. The CDF at 1.08 is 0.8599. Did you understand the answer for part C, my friends? So what is the probability of a standard normal random variable being less than minus 3.20? What is this probability, it asks. So for part D, it is actually not very hard. So I need to use the symmetricity as well. Okay, let me draw you a picture now. So this is my standard normal distribution, and I have this perfectly symmetric shape around 0. So you see how perfect is it. So I have 0 here. I have a perfect PDF. And I have minus 3.20 around here. And the question is asking me the probability of Z being less than that, which is this small area. Actually, that small area is exactly equal to the area on the left-hand side of 3.20, that is. And that is equal to 1 minus capital phi at 3.20. So I will subtract the total area on the left-hand side of 3.20 from 1 and find that area, which is going to be the same as that area because of the symmetricity. And for that, I am going to do this. Probability of Z being less than minus 3.20 will be equal to the probability of standard normal random variable being greater than 3.20, which is the positive counterpart of the same value. And that tail probability is calculated by subtracting the cumulative probability at 3.20 from 1. And in the table that you have, you can find the cumulative probability at 3.20 at the bottom as 0.9993. And we subtract that probability from 1 to get the area on the right-hand side, which is 0.0007. And the final part, what is the probability of a standard normal random variable to be between minus 0.98 and 0.49? Now, my friends, I recommend you drawing a plot diagram at all times. So I have the standard normal distribution. Once again, I am looking for the probability between minus 0.98, minus 0.98 is here, and I have 0.49, which is here, 0.49. So always draw a picture like this. Say that I want to calculate this area. That probability, my friends, is going to be calculated by subtracting the total area on the left-hand side of minus 0.98. So I'm going to subtract this white area on the left-hand side of minus 0.98 from the total area on the left-hand side of 0.49. So I will find this cumulative probability at 0.49, and from that I will subtract the cumulative probability up to minus 0.98, and that is going to give me the area in between. And for the first part, I can directly find the CDF at 0.49. At 0.49, it is equal to 0.6879. 0.6879 minus, I am going to calculate the second probability here, which is the probability of Z being less than minus 0.98. Now you know that due to the symmetricity, this cumulative probability here will be the same as the tail probability at the positive 0.98. And that tail probability will be calculated as 1 minus the CDF at Z, which is 0.98. And the CDF at 0.98 is what? Let's check that out as well. The CDF at 0.98 is 0.8365. And if I subtract 0.8365 from 1, I will get my answer, which is 0.5244.